Thank you very much to the organizers for inviting me here. And I'm Jutta Toscano from the University of Basel, where I work alongside the Village Group. And we try to understand how putting energy in different degrees of freedom of molecules can change their reactivity. And so we try to steer and maneuver chemical reactions 1 degree of freedom at a time, as the title suggests. So we work in the gas phase, so a little bit of a shift. But usually in the gas phase, we look at chemical reactions that happen between atoms and molecules that exist in a variety of quantum states, and they have different velocities, and it's a little bit like listening to an orchestra playing a symphony with all the instruments playing at the same time. So what we would like to do instead is to pick out individual instruments, such as selectively listening to the violin or the cello and try to understand the tune in more detail. So ideally, we would like to simplify the problem as much as possible. We want 2 species of which we know all of the properties, and we collide them together, and then we see how they react. But we have, of course, a lot of different degrees of freedom that we would like to control, or at the very least have very well defined. And in this talk, I'll specifically concentrate in the first part on the structural degrees of freedom, specifically regarding some Diels-Alder reaction between different conformers of molecules. And then the second part is more astrochemically relevant, is looking at the rotational degrees of freedom of the neutral molecules. And it's also worth pointing out that sometimes we can have a thermal distribution of some of these states. For example, following collisional cooling, like we will see for our ions. Or alternatively, we can non-thermally populate a single state. And that usually we either do by optically pumping with a laser to a specific state, or selecting out from a larger ensemble only the particles that react in a specific way to an external field, such as an electric field, like we will see for our neutral molecules instead. And so in general, we, in order to prepare the reagents and detect the products, the field of cold chemistries is developing a lot of different techniques, and we combine them in different ways to try and get as much control over all of these degrees of freedom as possible. And to summarize it, we can broadly categorize the different techniques that are used between electric fields, magnetic fields, and laser light. And which one we use in each specific case depends on the properties of the atoms and molecules that we want to control. So for example, whether they have a charge or a dipole moment, a magnetic dipole moment, they're polarizable. And you don't need to read this full list, but I'm just giving you a few examples of the techniques that are used in the field, just so that I can actually highlight the ones that I'll be referring to, which are electrostatic deflection and state preparation, as well as ion trapping and laser cooling. But if we start with electrostatic deflection, which is when we apply a very large inhomogeneous electric field to separate in space gas phase molecules that have a different dipole moment. And so in our case, we separate, for example, different conformers, so molecules that have a different dipole moment in virtue of the fact that some of the atoms point differently with respect to the rest of the molecules, and so they have a different dipole moment, or different rotational states, which have a different effective dipole moment due to the rotation of the molecule itself. But if we start with the conformers, I'll take as an example our favorite neutral molecule, which is dibromobutadiene. So this is a carbon chain with 4 carbon atoms and 2 double bonds on the side carbon atoms. And it has 2 bromines that can either sit on opposite sides in the central carbon atoms to give trans dibromobutadiene, which has no dipole moment. But if they sit on the same side, they give gauche dibromobutadiene, which has a sizable dipole moment of 2.3 dpi. And under standard conditions, collisions will scramble these because there is a single bond in between the central carbon atoms, so they can rotate. But we freeze them because we put them in a molecular beam, so we supersonically expand them, freeze the different conformers, and make a molecular beam out of a mixture of the conformers, and fly them through an electrostatic deflector, where we apply a very large electric field gradient, and the trans dibromobutadiene has no dipole moment, so it will feel nothing, and it will continue traveling down the molecular beam axis. But the gauche DBB will actually be deflected off the molecular beam course and will be peeled off so that we can actually separate them in space and then react either one or the other with our ionic target that we keep in our ion trap. And then we can look at how the reaction proceeds using a mass spectrometer. And before my time in Basel, they actually looked at the reactivity of gauche and trans DBB with propene ions. And so the dibromobutadiene reacts with propene to undergo a Diels-Alder reaction where you make a cyclohexadiene ring. And even though you might expect only the gauche to react because it's the only conformer that can actually undergo a standard canonical concerted Diels-Alder reaction where both bonds are made at the same time, they actually showed that both conformers reacted. And so the stepwise mechanism was also active at the same time. Now, they measured that gauche reacted about twice as fast because in the long range part of the potential, not only do you have an ion-induced dipole interaction term, but you also have a ion permanent dipole. So it's more attractive in the long range, but it was the first time you could actually measure that two different conformers kind of separated in space would then react differently towards the Diels-Alder reaction. So what we wanted to do is to also have conformation selected ions trapped inside our ion trap. And our molecule of choice in this case is meta-aminostyrene. So it's a benzene ring with, you can see here, a vinyl group that either points towards the amino group at the meta position for cis meta-aminostyrene or away from it in trans meta-aminostyrene. And in our ion trap, we don't just trap the ions, but we also want to cool them down. And in order to remove the extra energy, we embed them in Coulomb crystals of laser-cooled calcium ions. So you can see here a single calcium ion, and here is a larger crystal of 1,000 or so calcium ions that are continuously being laser-cooled, so they fluoresce, and so we can image them with a camera. And in a standard experiment, what we do is we form a Coulomb crystal of calcium, and then after we form that, we actually add other ions that are effectively, we use the calcium as a bit of a heat sink. And we add different ions, and in this case, there is some N2+ ions that accumulate in the center because they're lighter. But the aminostyrene ions that we are interested in are actually heavier. And so instead of accumulating in the center, they would be kind of delocalized around the calcium. So in this simulation, so these two are experimental videos, but in this simulation, the calcium is in blue, and there are some heavier ions in red. So the way that we put different conformational ionic molecules in our Coulomb crystal is by first making a Coulomb crystal like the one that I showed you before inside our ion trap and using the same setup as I showed you before, but without the deflector. And then we point a molecular beam that contains a mixture of the two conformers towards the center of the trap, where it gets intersected by the ionization lasers. So we ionize using REMP, resonance-enhanced multiphoton ionization. And the molecular beam and the REMP lasers actually intersect just below the trap center. It was quite important to make sure that the trapping and loading region were not exactly the same, so that we wouldn't fragment the ions that we just made. And so if this is our calcium Coulomb crystal, here the calcium represented in gray with the cooling lasers, we have a molecular beam with a mixture of conformers and the REMP beams intersecting just below. And we're very lucky that the different energy levels of the different conformers are not the same. And so we can use, by selecting the wavelength of the laser for the ionization, we can selectively ionize either one conformer or the other. And so, for example, if we decide to set our lasers to the frequencies for the cis meta-aminostyrene, we would make an ion down here, and as soon as the ion is made, we're pushed towards the trap center, where it will interact with the calcium. It will be sympathetically cooled through collisions, and it will be embedded in the crystal around the calcium shell in this green shaded area in the inset. And what we actually see in the lab is just a little squishing of the crystal after the loading. and the presence of a few other ions that we get. But once we actually take a mass spectrum, we can definitely see that we have our metaminostyrene at 119 atomic mass units as expected. And then we can go on to simulate what these crystals look like before and after the loading. And we can, in our simulations, we're not limited to just looking at the laser cooled ions. We can actually give a false color to the metaminostyrene ions, which are here displayed in green, and so sit around the calcium crystal. Right, so we can make either cis metaminostyrene or trans metaminostyrene ions, and these do not have enough energy to interconvert in our trap, because the energy that requires to turn around this bond and isomerize is more than 100 millielectron volts, which is not available. And so we can see that indeed we see that we have negligible trap losses over the course of about 10-15 minutes. And so this was the part about the conformers, and we're now ready to study fully conformationally selected ion neutral reactions. For the last few minutes, I would like to tell you about this new project that we have about separating different rotational states. And in our case, as you can see in this cartoon, para water and ortho water, which correspond to the, as lowest rotational states have the lowest rotational state of the para water is J equals 0, and for ortho is J equals 1. And so we can separate them using electric fields. Now, you might not think that adding a single quantum of rotational excitation can make that much of a difference to a chemical reaction, but there is actually a growing body of evidence that shows otherwise. And indeed, the addition of a single quantum of rotational excitation has been shown to increase the rate of ionization, such as in this reaction between H2 and metastable helium, also decrease the rate of reaction, as in water with N2H+, and also change the branching ratio of reaction between OCS and metastable neon. And so usually in collision-rich environments, this is irrelevant because they will get scrambling of rotational states, but in collision-starved environments, such as the interstellar medium, this can be important. And indeed, as we heard before, I don't think I need to try to convince you how it's important to use a set of observations to see what molecules we have in space and their abundances, and combine those with experimental studies where we measure rate coefficients and branching ratios to then input into models that can then predict certain amounts as a function of time. And then we can see whether these match what we observe, but we can also use them to guide our next experimental efforts to see what we need to study in the lab to refine our understanding of the chemistry of different parts of space. And indeed, what we'd like to contribute is to see whether the rotational state-specific reactivity could improve our understanding of the abundance of structural and spin isomers. And the reaction that we're concentrating on at the moment is a reaction of ortho and para water. And because this could tell us, for example, whether the preferential destruction of one or the other of the spin isomers could affect the ortho to para ratio of water in different parts of space. And so we want to measure the rate coefficient as a function of the rotational state of the water with C+ ions. And this actually gives the HOC+ and HCO+ isomers that we heard of before. But in our case, instead of looking at how they might be preferentially destroyed, we would like to see how their preferential production could affect the isomeric ratio that we observe, and that can tell us about the dominance of photo-dominated region or X-ray dominated region. So we will also want to measure the branching ratio of this reaction. And we will do this with the setup that I showed you before. We separate water using, making a molecular beam and using the deflector. And then in the lab, we just managed to make, to sympathetically cool C+ ions into our Coulomb crystals. And so hopefully soon we'll be able to tell how different is the tune of the reaction when we add a single quantum of rotational excitation. And with that, I'd like to thank Lei, who's the graduate student on the conformation selected work that I presented at the beginning, and Ashwin is a graduate student on the astrochemistry project, as well as Stefan and the rest of the village group. All of the support staff in Basel, without whom this work would not be possible, and all of the students and collaborators and you for your attention.